Hi there. Since we're discussing the thermal calculations of different semiconductor devices using the Plex simulation software, I wanted to create a separate playlist for some basic calculations of thermal loading of different semiconductor devices that could help us understand the topic even further. So here, today's topic is to calculate the junction temperature from the given transient thermal impedances. Here is a typical datasheet value of the transient thermal impedance with respect to the pulse width. Depending on what type of application we have, we might have a single pulse or a different type of duty cycles of power loading. And many manufacturers provide the datasheet with this type of characteristics. As you can see, one is given here with a single pulse here. The ZTH curve would follow the lowermost curve. If we have another 10% duty cycle in the loading, it could be the third from the lower side, this curve here shown in green. The target of this simple tutorial is to calculate the junction temperature of the semiconductor device. In this case, it is the TO-252-3 package. 4 different duty cycles here. I will assume different power losses, as this can be either measured or can be calculated from simulations or other theoretical calculations. I will assume that for the first calculation, now before I go into the calculations, as you also can see, there are different duty ratios. For the first example, I will consider a single pulse of power. That means let's switch back to the paper. So the target is today is the calculation of junction temperature from ZTH curve. That means from the transient thermal impedances. For the first example, let's consider a single pulse. In this form, so time is represented along the x-axis, and here we have the representation of power, and this is in terms of watts. It is also practical to have some applications where we only have a single pulse. That means this power is represented with this block. Now we would represent the width of the pulse to be Tp. If this is the case, we can calculate the transient thermal impedance from the graph, as I showed you shortly. But before that, to calculate the junction temperature, say for example, we have Tj. It should be equal to the sum of ambient temperature and the delta T. Now delta T is actually the rise of temperature caused by that impulse. That means I can write it to be Ta, the ambient temperature, plus the power, PV, that represents the total power loss for that single pulse, times the value of the transient thermal impedance for that pulse, or in general, a term T. That means we know at this point the value of Ta, we know the power. The only thing missing is that ZTH, which we need to calculate. I will assume that TP to be 0.1 seconds. That means the width of the pulse is 0.1 seconds. And that would give us a particular value of ZTH from the datasheet value. As you can see, so 0.1 seconds. Let me take another color. So 0.1 second is here. This is the width of the pulse, so to speak, pulse width. And this would represent, now there are a bunch of curves here, but we need to consider single pulse since there is no periodical application of the power. In that case, it's single pulse with the lowermost curve. At 0.1 seconds, we would read here. And that would give us a value of 1, 2, 3, 4, 5. So this curve is then giving us a value of 5 here. And the unit is degrees Celsius per watt. So we can continue the calculation with the red values now. So this would correspond to a ZTH value of 5 degrees Celsius per Kelvin. Watt. The degrees Celsius per watt, or it's also written as Kelvin per watt. Both are okay. Now the only thing remains is to calculate the TJ. The ambient temperature, I assume it to be 25 degrees Celsius, plus the power, let's consider to be 10 watts. And we have the value of ZTH to be 5 degrees Celsius per watt. That's 25 plus 50 should give us then 75 degrees Celsius. And this is exactly what our target parameter was. So this is the junction temperature for this particular pulse width, 0.1 seconds in this case. Now if we consider another application where we say we have a pulse width of 1 second with the duty ratio of 10%. How should it look like? So let's say this was example 1. We'll consider another example. So here we will consider a 10% of duty cycle. That means our power will be applied after a certain point. Then only 10% of the time it's conducting. And then there is no power at all for 90% of the remaining time in one period. Then again comes another pulse, then for 10%, and then this continues. Infinite. So this is again TP or T in general, pulse, TS, and this is power in terms of watts. Let's continue with the calculation. So I think this is better to represent as a general term T, because our TP would be then this width, TP. And if you want to show the total period, it is capital T. So duty ratio 0.1 seconds. Sorry, the 10% is 0.1. That would represent, for our case, it's TP divided by time. time period. So this is written accordingly. In this calculation for this particular application, I would consider the power loss to be 2 watts. So for example, this max value is then 2 watts. And the duration of the pulse is given to be, let's take it 1 second. And PV is 2 watts. Then it's a very simple calculation again. We need to calculate the ZTH first. Let's bring back the datasheet. We said this green one represents then our ZTH curve for 10% duty cycle. It was here for the previous one. No, this one was previous one. And for 1 second, let's read the value. It is here. And it represents around 9.4. So ZTH, then I would write corresponding to TP is equal to 1 second. We have ZTH is equal to 9.4 degrees Celsius per watt. The only thing that's remaining is to calculate the T junction. Let's assume an ambient temperature of 60 degrees this time. So 60 degrees plus P, which is 2 watts. And we have ZTH 9.4 degrees Celsius per watt. So this should be 18.8 plus 60, so 78.8 degrees Celsius. And this is again what we wanted to calculate. I would like to calculate for one more case, which is a little spatial for our calculation. So I'll call it example 3. At this point, we will have an offset as well in the pulse of power. So this particular case includes 2 parts in their pulse. One is the steady state and another one is the transient state. Let's draw it first. So I will not give a numerical solution for this example. I'll just give you a general procedure how to calculate in case we have this type of loading. As I said, the first part was a steady state operation. That means the type of offset. And then comes our transient operation for a certain period, like this. And then it repeats itself periodically. So let's say period was here. So it continues this way. Let's take another. This is T. So normally the loading is in terms of current. Let's take the loading in terms of current. That's ampere. And this is seconds. Let me change the color. So here is our pulse duration TP. And this part should represent the time period T. Now the duty, as I said, we can calculate from D is equal to TP by T. Depending on what duty cycle we have, we can go back to the datasheet and read the value. Important here is, though, we have two different values here. Let's say here we have I1, which is steady state, and we have I2, which is represent the peaks of the transient ones. There will be two different or two levels of temperature rise. One would be at this time, at this shift level, so to speak, and let's represent this one with delta T1. The second temperature rise would be during the transient period, and let's represent this one by delta T2. For the calculation of the total junction temperature of the semiconductor device at consideration, we need to also consider the power for these levels. So let's see for the steady state, this is steady state, and this is transient. So for transient, we have to calculate the power as well, P2. Actually, it is from here, from this reference level. So this total is then P2. That means for the temperature rise, delta T2, we need to consider the difference of 2. So P2 minus P1. This would give us the power for this particular part. Say for current I1, we have a power loss of P1, and for current I2, we have a power loss of P2. If this is the case, we can calculate the temperature of the junction as follows. T junction is equal to ambient temperature plus delta T1 plus delta T2. TA is known. For delta T1, we need to consider ZTH. Let's call it ZTH1 for that steady state part, and the power is known or measured or calculated to be P1. For the second part, that means for the transient part, we need to consider again the ZTH. Let's say this time it is ZTH2 times the power of the transient part, which is P2 minus P1. That's it actually. So for a particular duty ratio, we need to go back to the datasheet, read these values of ZTH, input this here. And the power calculations, as I said, it should be from measurement or from detailed calculations. Another point I almost forgot to mention about the reading of ZTH and ZTH1 and ZTH2, depending on which state of operation we consider. So this is very crucial, and actually this was the main reason I wanted to record this tutorial. For this steady state operating point situation, we need to read the RTH value, that means this final value of the ZTH curve. This is what I mean. So for steady state operation, as we know that the final state of operation would be then this value, this region here. And this would represent the RTH, the final value of the ZTH, so to speak. So we can also write it this way for steady state. You know that it's a limit, time tending to infinity, ZTH of t is then equal to RTH. So that means for steady state, for this part, we need to consider the RTH. And for the second part, which is the transient one, and we also have a certain duty ratio for that part as well, that we need to consider that particular part. If it is 25% or any other duty cycle, we just need to go there and read the corresponding value of ZTH. That would represent then, for this particular duty cycle, the ZTH of the transient operating point scenario. And then we input the value here, and the sum of the ambient temperature plus delta T1 and delta T2 gives the total junction temperature. So this is the crucial part. Don't forget this one, and I hope it's clear enough for understanding. I will continue our discussion with more examples later, but thank you for watching, and let me know for any questions you might have.